So I think we're ready to continue. Our speaker is Krystian Gajdzica from Krakow, who speaks on arithmetic properties of the restricted partition function. So please go ahead.
Thank you very much for introducing me, and great work you are doing during the conference. Today, I would like to say a few words about the theory of partitions, in particular, the theory of restricted partitions. So at the beginning, I would like to define restricted partitions. To do that, let us assume that curly A is a sequence of positive integers. K is a positive integer, and n is a non-negative integer. By a restricted partition lambda of n, we mean each non-increasing sequence of positive integers lambda 1 up to lambda j, which belong to the multiset a1 up to ak, such that their sum equals to n. It is important that indeed we deal with the multiset because we do not have any additional assumption on the sequence A. Therefore, it may happen that there exist, for instance, A1 and A2, which are the same, but we want to distinguish them in some way. So we may assume, for instance, that we are give them a distinct colors. In such a way, we want to distinguish. But if we define the restriction partition, then we can ask how many such a partition exist for a given positive integer n. Therefore, we may define the restricted partition function P of nk, which counts all such partitions. Moreover, we may extend the restricted partition function to each integer n in the following way. If n is negative, then we put that P of nk equals 0. And if n equals 0, then we put that the function equals 1, because the empty partition is the only one in this case. It amounts to maintaining that for a sequence of consecutive positive integers a1, if we put k equals infinity, we obtain the classical partition function P of n, and we will use the traditional denotation, not this one, but the classical P of n. So let us take a look on the example of the restricted partition. Let us consider the case of plane partitions. So let A be a sequence of consecutive positive integers such that each positive integer j appears in j distinct colors. For instance, 2 appears in blue and red. And let us fix k equal to 10. Then for a given positive integer n, we consider only those partitions of n which part belong to the multiset, or which consists of 1, 2, 2, and so on up to the last 4. So for instance, if we put n equals 4, then PA of 10 equals 13, because we have the following possibilities. For more information, for more details about the classical theory of partitions and the plane partition in particular, I highly recommended the book written by Professor George Andrews, Integer Partitions and the Theory of Partitions. But today I would like to say a few words about the arithmetic properties of the restricted partition function. So let me remind that there is a well-known conjecture in the theory of partition which states that the odd density of partition function is 1/2. That is the limit as capital N goes to infinity of the cardinality of the set of those n smaller or equal to than capital N, such that P of n is odd over capital N equals to 1/2. Today, I would like to try replace the function p of n by the restricted partition function, and add at the beginning limit as k goes to infinity, and ask whether the same conjecture makes sense, or we should add some additional assumption to ask to state this a similar problem in the theorem of the restricted partition function. So it is the one goal of this talk, and there is another one which is connected with the result obtained by Karhatkar in 2019 for a sequence of consecutive positive integers. He proved that the restricted partition function in this case is bounded from below by 1 over sum of the first k positive integers, and from above by 2 over 3. This inequality holds for infinitely many values of k, but more precisely, actually the lower bound holds for all values of k. Yeah, so I will try to generalize this result for all sequences of positive integer a. To do that, we need to use well-known or very useful theorems related to the restricted partition function. The first of them is the recurrence relation of the restricted partition function. That is the following: if we fix not positive, non-negative integer n, positive integer k greater or equal than 2, and any sequence of positive integer a, then we have that the restricted partition function p of n k equals pa of n minus a k plus pa of n k minus 1. This equality can be easily proved because, well, if we consider all partitions of n, we actually have two possibilities. We can take the part ak, or we do not. If we take the part ak, then we can consider n minus ak or restricted partition of n minus ak with parts in the multiset a1 up to ak. So this summand is responsible for this situation. And we can also have the situation in which we do not take the element ak. So then we consider the cases of partition in which we use only the elements of the multiset a1 up to ak minus 1, and this function is responsible for this situation. For k equals 1, it is clear that this function pa of n1 equals 0 if a1 does not divide n, and 1 if a1 divides n. Okay, I have also added the assumption. And the next theorem is related to the periodicity of the restricted partition function modulus some positive integer m greater or equal than 2. And this is the following theorem. So let us always curly a be a sequence of positive integers, k and m be a positive integers, and m be greater or equal than 2. Then the function p of n k modulo n is periodic on n with period m to the power k minus l minus 1 times least common multiple of a1 up to ak. In many ways, this period is not a fundamental period, unfortunately, but it is very important theorem despite this fact. Because if we want to determine the asymptotic density, or simply density of the set of those positive integers n for which pa of nk is congruent to I modulo m, it is enough to check the values of the restricted partition function over a finite range of n because of the periodicity. From this two theorems, we can deduce upper bound and lower bound for the odd density of the restricted partition function. The upper bound is the following. For any sequence of positive integers, the odd density of the restricted partition function p of nk is bounded from above by 2 over 3, And this inequality holds for infinitely many values of k. More precisely, if this inequality does not hold for some k, then it is automatically satisfied for k plus 1. In the case of lower bound, we can give a bit more general version of the theorem, because we can fix positive integer m greater or equal to 2, and then for each positive integer k, we have that the density of those positive integer n for which the restricted partition function is not congruent to 0 modulo m is bounded from is greater or equal to than 1 over the sum of the first k elements of the sequence A. It is worth mentioning that both of these theorems are not optimal. The first of them mainly because 2 over 3 does not depend on the sequence A at all. The second one depends on the sequence A, but it is independent on the value of m, so it is not optimal as well. So we have just achieved the first goal of the talk, and now it's time to focus on modifying the well-known conjecture to the case of the restricted partition function. So let us consider the so-called restricted Mri partitions. That is when, let us assume that m is a positive integer greater or equal to 2. And now we consider the sequence curly m to be a sequence of consecutive powers of m. And now our recurrence relation takes the following form. Moreover, it can be proved that the sequence Pm of nk modulo m is purely periodic with period m to the power k. From this assumption and this observation, we can deduce an analogue of the well-known theorem of unrestricted Mri partition. That is the theorem which states that for given positive integers k, n, and m, such that if we represent n in base m, that is n equals to the following sum, and we put curly m to be the sequence of consecutive powers of m, then the restricted partition function Pm of nk is congruent to the product over j from 1 up to k minus 1, Cj plus 1 modulo m. In the case of unrestricted partition function, unrestricted Mri partitions, we have infinite product in this place. This theorem is really fine because from it we can easily deduce the following characterization. Let us assume that m equals 2. So let us consider the restricted binary partitions. Then we have that the restricted partition function Pm of nk is odd if and only if n is congruent to 0, 1 modulo 2 to the power k. Great. So if we assume that k is greater or equal than 4, then we obtain that the density, the odd density of this restricted partition function is 2 over 2 to the power k. So it is 1 over 2 to the power k minus 1, and it is smaller than 1 over 2. Therefore, we cannot simply replace classical partition function by the restricted partition function in the conjecture. We need to add some additional assumption. We will talk about it a bit later, but let us also consider the case in which the curly m is the sequence of consecutive powers of 3. Then if we represent n modulo 3 to the power k in the base 3 in the following way, then we have the following characterization. The restricted partition function P of k is congruent to 1 modulo 3 if and only if the number of non-zero coefficients C1 up to Ck minus 1 is even, and all of them are equal to 1. Symmetrically or similarly, Pm of K is congruent to 2 modulo 3, if and only if the number of non-zero coefficients C1 up to Ck minus 1 is odd, and all of them are equal to 1. It's worth mentioning that there are similar descriptions for the sequences of consecutive powers of 4 and consecutive powers of 6, but they are a bit more complicated, so we will not talk about them today. Okay, great. So let us add some notation. So let n be greater or equal than 2, k be greater or equal than 1, and I be a number from the set of 0 up to n minus 1 be fixed. And let us assume that curly A is a sequence of positive integers. We define the set S curly A I and k as a set of those positive integers n, such that PA of nk is congruent to I modulo n. And we also define for the restricted Mri partitions the function R curly M I and k as a cardinality of the set of those n modulo n to the power k, such that P of m and k is congruent to I modulo n. Today I will not talk a lot about this function. Actually, I will not say anything, but for anyone who is interested in some properties of this function, I encourage to visit arXiv and take a look on my preprint and on the restricted partition function. But we have there is another interesting theorem that states that the limit as k goes to infinity of the density of those positive integers n, such that P m of nk is congruent to 0 modulo n, is equal to 1. So if we replace 0 by I for I from the set of 1 up to n minus 1, then the limit is equal to 0. So we have the following theorem too. And now I would like to finally show some numerical computation related to the odd densities of the restricted partition function. So let us define the following sequences. Let AD be a sequence of consecutive diff powers of positive numbers, positive integers, S to be a square non-negative integers increased by 1, H to be a sequence of hexagonal numbers, T to be a sequence of triangular numbers, and P to be a sequence of pentagonal numbers. Then numerical computation made in Mathematica shows that the odd density for these sequences seems to goes to 1/2 as k goes to infinity, because the values are very near to the value 1/2. So the question arises, what is the difference between these sequences and the sequence of the consecutive powers of 2? It's very clear, because these sequences have infinitely many prime divisors. So maybe the following problem makes sense. Let us assume that curly A is a sequence of positive integers such that greatest common divisor of A equals 1, and the set of prime divisors of A is infinite. And the question is, does the equality as limit as k goes to infinity of the odd density of the PA of nk equals 1/2? Hold, as the first question. And as a bonus, I have additional computation in which I replace 2 by n for n equals 3, 2, or 3, 4, and 5. And I consider only the case in which the sequence A is a sequence of consecutive squares numbers. I obtained the following results. We have the following table, and let us notice that for a fixed positive integer m and the remainder I, it seems that these values goes to 1 over m for each remainder I. Therefore, we can state another one question, but before we do that, let us there is at least one another interesting observation from this table. Let us assume for a moment that k is even, and take n and I, and also n and n minus I. So for instance, let us assume that n is equal to 3 and I is equal to 1, and then n minus y and n minus I is of course 2, and we have that these values are actually the same for I and n minus I. The same holds for the case in which n is equal to 5. So maybe there are so we may state another two questions: whether does the following equality hold? That is, the limit as k goes to infinity of the density of the set of those positive integers for which PA of P of nk is equal to I modulo m over n is equal to 1 over m for n greater or equal than 2, and I from this 0 up to n minus 1. This is because I have also checked the values for the other sequences, for the other powers, not only for 2 but for the higher 2. And the last question: does the formula the density of SAD JMK equals the d of SAD m minus j mk called for any fixed parameter k n greater or equal than 2, and j from the following set for k for even values of k. And I think it is the high time to end. Thank you very much for your attention. It's an honor for me to give a talk during such a great conference.
Thank you very much, Krystian. Are there any questions for our speaker?